Welcome to part 3 of the laser tutorial. Now I'll start off by saying this part is not mandatory and is a bonus to the other ones. In this tutorial we'll be looking more at visuals like pulsing laser, sound effects and particle effects. You'll see the result on the screen now, showcasing the different results and different effects you can see and the sound as well with it. Most of the stuff can be done separate, so I'm going to be leaving timestamps below if you only want to do a particular effect. We'll be continuing off from where we left last time, and we're going to start by creating a means of grabbing an object. We can start off by creating a folder we'll name hold object. Once you've created the folder, open it up and create a blueprint class. For the parent class, we're going to select actor component, call the new actor AC hold. Next is the input. Start with a input mapping context. Call it IMC interact. And the last piece for holding an object, we're going to create an input action. Go ahead and call it IA interact. Open up the input action, and inside the trigger press the plus button and swap none to pressed. Save and close IA interact and open up the input mapping context. Add a new mapping with the plus and set it to IA interact. Select whatever key you want. I'm going to choose E. Save and close, and we're done with the input mapping context. Next up is the logic for holding the object. So open our actor component. We're going to start off by creating our input mapping context. We can remove the event tick, then get a reference to our player controller. From the player controller we want to get enhanced input. From enhanced input we're going to look for add mapping context. Attach the newly created node to begin play. For the mapping context, select our IMC interact. Next up, we're going to create the 3 variables we'll be using for held objects. The first we'll call held object slot. For the type, we're going to select static mesh component. The next variable is going to be a reference to our physics constraint, so we'll simply call it physics constraint. The type of this variable will be physics constraint component. And finally, we're going to need a reference to the held object. The type of the final variable will be primitive component. Now that all our variables are set up, we're going to start with the logic. We'll search for our IA interact. Before continuing off our IA interact, we're going to create the necessary functions. The first function will be called trace for pickup. This function will take in 3 parameters. The first called start location, switch its type to vector. The next parameter will be called forward vector. And the final parameter will be called range, and switch it to type float. We can set the default value of range to something around 300. Next, go back to the event graph and place our new function in front of the triggered of IA interact. We're going to set the function up by first getting the player camera manager. From camera manager, we're going to get actor location and attach it to start location. Next, from Camera Manager, we want to get actor forward vector and attach it to forward vector. We can leave range at its default value. Next, before I forget, in begin play we're going to set our 3 variables. To start, we're going to search for get owner, and from get owner we're going to get component by class. In the component class we want to select physics constraint and then drag our physics constraint variable and hold Alt to set and attach our return value to it. Now with our physics constraints we're going to search for get parent components and we want to get a copy of the first index. From the get we want to cast to static mesh component. On a successful cast we want to set our held object slot. With our variables set up now, we can head back into our trace for pickup. The first thing we want to do is determine whether we want to pick up an object or drop it. So we get a reference to our held object. By right-clicking on held object, we can convert it to a validated get. On valid, we want to release our object. So we're going to create a function called release object. We'll also take this opportunity to create the other function called pickup object. Pickup object will need to take in one parameter, which we'll call hit results, and its type will be hit result. Now we can return back to trace for pickup and place release object in is valid. For is not valid, we're going to need to check if there's an object in front of us. So to do so, we're going to add a box trace by channel, connect to is not valid, and then we're going to use our parameters to set up the box trace. Let's get start location and attach it to start. For end, we're going to drag from start location and add. Then we're going to grab the forward vector and multiply it by the range parameter. We will then attach the result to the addition that we created earlier for the endpoint. And finally set the half height to 20, 20 and 20. From the box trace we first want to check if we actually hit something, so we add a branch, and on true we add our function pickup object. Don't forget to attach the out hit to the parameter. Now we need to set up our 2 smaller functions, release object and pickup object. Open up release object and drag a reference to physics constraint, and from that reference type break constraint. After break constraint, we want to set held object to null. That does it for the release object. Next is the pickup object. Inside of pickup object, we want to start by breaking our hit results. From there, we want to drag from hit components and search for is simulated in physics. Add a branch and connect its condition to is simulated in physics. And then get a reference to physics constraint and held object slot. Drag off physics constraint and search for set constrained components. Attach held object slot to component 1 and attach hit component to component 2. You can also attach hit bone to component bone in the event that you grab a physics actor with bones. All that's left to do now is to set our held object to the hit component. and we can just tidy this up so that the nodes look a bit easier to read. With this function finished, we've now completed all the work that needed to be done in AC hold, so we can close the blueprint. Next up, for the final pieces we need to add for the grab components, we need to open up the first person character. Inside of the first person character, we're not going to be doing any blueprints, we're just going to be adding a few components. We're going to be adding the two variables that we created in our AC hold here inside of the player character. To do so, we're going to start with a sphere component, which we're going to attach to the first person camera. We can rename this sphere to a more appropriate name like anchor. With anchor selected, we're now going to add another component, which is the physics constraint. Now we're going to set up all the different parameters and values for each of these components. We'll start off by selecting the anchor component. First off, make sure the location is 10, 0, and -60. Next, scroll down to the collision preset. We want to select collision preset and change it to no collision. We can also disable generate overlap events. And next we want to go down to rendering and set visible to false. Next up is the physics constraint. Inside of the physics constraint, we're going to look for linear limits and set all three of the options to free. Then scroll down all the way to linear motor. Inside linear motor, we want to set position targets all to true and set strength to 500. For velocity target, we'll set all of them true as well and strength to 100. Next is angular motor right below. We're going to start by swapping angular drive mode from S-lerp to twist and swing. Then inside of target orientation, we want to set twist and swing to true and set strength to 500. And for target velocity, we want to do the same, twist and swing to true and strength to 100 this time. And with that, both of the components have been set up. All that's left to do is set up our actor component inside of the player character. To do so, we add component and search for AC hold. Now we can go ahead and run the project to test if we can pick up an object. So now that we're inside the editor, let's try and pick up our laser cube, and there seems to be an issue. So there are two things causing the issue. The first one is inside of the first person character, so let's open that up. Inside the first person character, select anchor and go down to the collision presets and set the preset back to block all dynamic. We can then set the collision responses to ignore. The important part is to keep collision enabled for query and physics. Once you're done with that, you can close the first person character, and we're going to now open the laser cube. Once you've opened laser cube, we need to select our static mesh component and scroll down to physics and get the advanced drop down and open it. Inside, we want to swap the sleep family from normal to sensitive. That's the only change we have to make here, and now our grabbing system will be fully functional. The reason we have to change the sleep family is because normally, when you create a gravity gun like this, for instance, you'll use the event tick to wake up the physics component. But we're not doing that, and to avoid doing that, we're just using the sleep family and changing it to be more reactive. With that, we just finished our first part of this bonus tutorial, which was picking up our laser cube. Next, we're going to be working on the materials for our laser. To start this, we're going to go into our lasers folder and create a new one called materials. We can start by moving our M laser into that folder. Let's also take this chance to create our visual effects folder and sound effects folder. The first material we're going to make is a very simple one. It's going to be for our laser hit. So create material and call it M_decal. And then we can open it up. The first thing we need to do is we need to swap the material domain from surface to deferred decal. So go ahead and select that. Next up, swap the blend mode from opaque to masked. Sorry, not masked, but translucent. Next, hold down 4 and left click to get a vector 4 node. Right click and convert to parameter and call it color. Select the default color of your choice and then plug it into base color. Hold down M and left click to get a multiply, connect A to the color and set B to 100 before connecting it to the emissive. Hold down left click and T to get a texture sample and connect it to the opacity. For the texture, we're going to look for sphere render mask. And that's the first material done. Feel free to close it after applying. The next material we're going to be making is the heat distortion effect. We'll later be applying this material to a particle effect. So inside the same folder, we're going to create a new material and call it M_heat distortion. Open the material up and with the default parameters selected, swap our blend mode from opaque to translucent. Swap the shading mode to unlit and tick two-sided. Hold 1 and left click to get a float value and connect it to opacity. Then we want to get a texture sample, so hold down T and left click. For the texture, we're going to search for T_water_LF_normal. In the UV, we're going to want to add a panner node, so hold down P and left click. Connect the panner to UVs, and in speed on the Y, we want to set it to 0.2. Next, we're going to want to call a linear interpolate, so we're going to hold L and left click. Attach B to RGB of our texture sample. Hold down 3 to create a vector and set Z to 1 before connecting it to A. Take the resulting lerp and connect it to the normal. Don't worry if it stays grayed out like mine, it's going to change once we connect the refraction. Now we're going to deal with the refraction, so start by getting a texture coordinate node. Hold down 2 and left click to get a 2D vector. Set the 2D vector to 0.5 on both the X and the Y. Create a sphere mask and connect A and B to texture coordinate and the 2D vector we just made. Set the radius to 0.5 and the hardness to 0. From the sphere mask, drag a power node and leave it as is. From the power node, we want to get a clamp, which we're going to leave at min 0 and max 1. And we're going to connect this clamp to our alpha of the linear interpolate. We're also going to create another lerp, which we're going to drag from the clamp and set A to 1, B to 1.1 and connect the result to the refraction. And once you've connected the refraction pin, the normal pin should light up and no longer be darkened. Apply the changes and that will do it for the heat distortion material. The heat distortion may not be very visible in the viewport, so what we can do is we can open our level editor and just add a plane and apply our material to it to see the effect. Once we've applied the material, we just rotate it to be vertical and we can see that there's definitely some kind of distortion happening with our material. Next, we're going to be redoing our M_laser, so open that one up. The effect we're going to be trying to achieve with our new material is to have it be pulsating, so the laser isn't just a standard one color with one level of emissive. We're going to start by adding a named reroute node called base color. We're simply going to take our color parameter and drag it into base color. We can move it out of the way because now we can reference our color with this new reroute node. Next, we're going to create another named reroute node and we'll call this one world position offset. There's no need to connect the new node to the world position offset as we're going to actually need to move it down later. Next, we can move our intensity parameter to the side and we're going to rename it to intensity pulse. And we're going to duplicate and rename the second one to intensity normal. Once the two new scalar parameters have been set up, we want to connect them with a lerp and connect them to A and B. For the alpha, we're going to create a new named reroute node called pulse lerp. First, we create pulse lerp and then we search for it to attach it to the alpha. We're then going to connect this lerp to our multiply for the emissive and search for base color for the A. Let's just reorganize these nodes a bit before moving on to the world position offset and the pulse lerp. We can also attach the base color to our base color. We're going to drag pulse lerp and world position offset a bit lower because we're going to need a bit of space to work on these two reroute nodes. We can quickly attach world position offset to its pin. Actually, quickly before we go and start our world position offset and blurp pulse, we want to go back to intensity pulse and intensity normal and set them respectively to 80 and 30. Now we're going to start what will most likely be the hardest part of the materials we're going to be making, which will be the pulse lerp. The first node we're going to get is a per instance random, followed by a time node. We want to add these two so that we have a random time for each different laser. Now search for a texture coordinate node and drag out and search for panner. Connect our add node to the time pin. For the speed pin, we're going to need a float value, so hold 1 and left click, and a scalar parameter value, which we'll get by holding S and left clicking. Set the default value to 1, call the parameter speed, and attach the two together with an append vector node. Make sure to not use the append many, but the append vector node, which we can then attach to the speed pin on the panner node. Now drag out from the panner node and search for texture sample. Make sure to connect the panner to the UVs and then search for cylindrical height map for the texture sample. Once we have a texture, we want to multiply it by 1.05. We then want to invert the black and white values, so we do a 1 minus node. And normally the result should look something like this, a black line in the middle with a gradient towards white. Next we want to use seal to sharpen the line. And finally, we're going to need one last scalar parameter, so hold S and left click and call it wave. Now we can fetch our pulse lerp node and attach it after the seal. Select our wave parameter and set its default value to 1. Now if we look at our material viewport on the left, we can see it flashing between our two intensities that we set earlier, now that pulse lerp has been set up. So to seal the deal and make an actual pulsing effect, we're going to need to do one last thing. From pulse lerp, drag off and create a linear interpolate and attach to alpha. For B, we want to drag off wave and multiply by -1 and then attach it. From the lerp, we want to drag off and get another multiply, and for B, we want to get a vector normal world space. And with that, we've finished our two named nodes. We just need to attach the world position offset at the end. Now, if inside the viewport we swap our sphere mesh to a cylinder, we can see it getting larger as the beam goes upwards, which is the effect we'll be applying to our lasers along their length. We can now apply the changes and close our M_laser material as we've finished with it. With that, we've finished with the materials and we'll move on to the laser blueprint. Before going any further, we're going to have to go and download a static mesh that's more adapted to the current material we made, as due to it affecting the vertices with the normal world space node, we actually need to have vertices to move. And the static mesh we are currently using does not support that, as it's simply a cylinder with no vertices along the height. So I went ahead and created a very simple one in Blender, and I've put a link to it in the description. Once you've downloaded it and imported it into Unreal, feel free to start the video again. As you can see, with our new static mesh, the mesh deforms as the pulse goes upwards. Now we want to open up our A laser blueprint and select our SM parent and replace SM cylinder by laser cylinder. We also need to change the scale from 0.05 on the X and Y to 0.1, and we can see inside the viewport that everything is functioning correctly. Let's compile and save the blueprint before heading back into the editor to run the project to see if everything is functioning as intended. Let's just remove the static mesh we used for testing and run the project. So as we can see, the laser does seem to be pulsing, but it seems to be very thin compared to what we saw in the viewport. So the reason for this is inside of the update that we made for the lasers. Inside set endpoint, we also scale the mesh, but to 0.05, so we need to swap that to 0.1. After running the project, everything is still pulsing and the correct size now. With that done, we've just finished the new laser. Now we're going to move on to the sound effects, or at least importing them for now. So open up the content browser and we're going to go into the sound effects folder. For the sound effects, go ahead and download the link in the description, which will lead you to kenny.nl, which will have a library of free sounds. I used these 4, which we've written here on screen. Feel free to use the same or whatever you choose. Pause the video if you need some time to download the assets. Don't forget to rename them so that you don't get confused with which ones I'll be using later in the project. Open SW Laser Hum and swap the volume from 1 to 0.02 and tick the looping box. Next is the laser impact, which we'll be also doing. Change the volume to 0.05 and check is looping. And finally, the power down, which will be setting its volume to 0.3. And power on, which will be setting to 0.5. Before moving on to our laser blueprint update, we're going to add a sound attenuation blueprint. Call it SA_lasers and open it up. Once inside, we want to swap the inner radius from 400 to 300 and the fall-off distance from 3600 to 3000. With this, we've finished setting up our sound effects, so we're going to move on to updating our laser blueprint. The first change we're going to be making is a function inside of the A-laser parent, so go ahead and open it. Call the function activate/deactivate. The function takes in two parameters, the first called sound and of type sound base, and the second called scene component of type scene component. This function will mainly be used to call the sound effect powering up and powering down. We'll start by adding a branch node and attach our active variable to the condition. Add spawn sound attached to true. For the sound pin, we want to get our sound parameter, and for the attached component, we want to attach it to SM_parent. So get a reference to that and connect the two. We can copy paste the spawn sound attached and attach it to false. Actually, now that I think about it, we can simply put the spawn attached before the boolean so that we only have to place it once. So let's just go ahead and do that. Let's not forget to remove the one attached to false as well. So now from the true and the false, we're going to want to get our scene component parameter and check that it's valid. We'll do that by right-clicking on our scene component and selecting convert to validated get. We want to activate our component. We'll then do the same on the false, but instead of activate, we want to deactivate. With that, we're done with the laser parent and we want to go back to our A laser, and more specifically, set endpoint. Once inside, we're going to select everything that is related to the set world scale 3D and convert it to a function. Make sure you detach L-head actor first, otherwise we'll create an output we don't need. And deselect L-range as it's a local variable. We'll call the new function update laser size. We'll need to break off hit info again so that we can reconnect it to hit actor. Let's just quickly tidy up our update laser hit by connecting our L-hit info to the hit and renaming it to hit result and range for the parameters. Next up on the list of changes, we're going to be reorganizing, or more like sorting into blueprints, the different scenarios we can encounter with the laser. So let's get to it. We'll start by selecting everything off of the false part of the branch that compares our previous and current hit actor. Make sure you deselect L-hit info and L-hit actor as their local variables to this function. Once you've deselected them, right-click and collapse to function. Name the function different actor hit. And rename the parameters to hit actor and phit information. Now we'll do the same with the true part of the branch. So select all the nodes and make sure you deselect the L-hit info. Right click and collapse the function. And then we can rename the function to same actor hit. Remove the second hit result parameter as it's unnecessary because it's the same value. And now we can move on to the final of the 3 collapses that we're going to do. We're going to move back to the initial one where we hit nothing. By that I mean we go to the validated hit for L hit actor and go on the is not valid. We once again select everything and make sure to deselect L hit info. Then we right click and collapse the function. Call the function nothing hit. Let's restructure the nodes so that it's a bit more tidy. And once we're done with that, we can compile and we see an error. So the error is coming from our different actor hit. So the reason for these errors are likely due to the local variables still being inside of the new functions we made. So inside of different actor hit, we want to go in and swap L hit actor to actor hit. We can also call the parameters for laser bounce instead of dragging the lines across. We can compile to see if the errors have been solved, and they haven't. We still have an error inside of the same hit actor. The error is caused by the fact that we have a break hit result without actually feeding it a hit result. So once again, we get our parameter hit result and attach it to the breaks. Now that all the errors are fixed, we're going to move on to making some new functions that will be mainly affecting the VFX and sound effects. The first function we're going to be making is designed to move the VFX of the burning. So we'll call it update location burn VFX. Function will take in one parameter of type hit result, which we'll call hit result. Now that we've created our function for the location of the burn, we want to add our audio for that effect. So go into add and select the audio components. In the details panel, set the sound to SW_laser impact. Go into attenuation settings and select our SA_lasers. And to finish, we want to make sure that auto activate is disabled. Next, add a second audio component. Which we'll call audio_laser hum. Inside of the details, set the sound to SW_laser hum and attenuation settings to SA_lasers. Compile and go back into the editor and run the project, and now we'll be able to hear our laser humming once we start. Let's go back into our A-laser blueprints, and now we're going to start adding the visual effects. So we're going to add 2 Niagara System components. Name the first system to NS_heatwave. And the second to NS_burn. Before going any further with the blueprints, we're now going to make our particle effects. So we head into our VFX folder inside the laser folder. Inside we're going to right click and create Niagara System. Select new system from selected emitters and click next. Select the hanging particles and click plus and finish. Let's rename the particle effect to NS_heatwave. Open the Niagara System up and we'll start by creating our user parameters. So the first one we're going to make is a float, which we'll call spawn rate. We'll set its default value to 1. Next, we want to make a vector parameter, which we'll call box size, which we'll set by default to 0 on the X, 0 on the Y, and 1 on the Z. Now we're going to start modifying our hanging particle. So we'll start by going into the emitter state and setting loop duration to 3. Then inside spawn rate, we're going to get our user parameter for spawn rate and drag it to the spawn rate. Next, go into the initialized particle. Set the lifetime mode from random to direct set and set the lifetime value to 3. We also want to change the sprite size mode from random uniform to uniform and the value to 200 instead of 10. Change the sprite rotation mode from random to direct angle degrees and leave the degree at 0. Next, inside the shape location, we want to change the box size to our box size parameter. So go ahead and drag that onto the box size. For the box midpoint, we want to reset to default value. Next, we want to go and disable the wind force and aerodynamic drag, or delete them if you prefer. So delete the scale sprite size and scale color, as we don't want to be changing either the size of the heat wave or the color as it's translucent. To finish our first effect off, we want to go into sprite renderer and change our sprite to our material called heat distortion. Once we've done that, we can apply our changes and the effect is done. Once you've saved the particle effect, open up the content browser, right click and select Niagara System for the second one. Once again, new system from selected emitter, but this time we want fountain and directional burst as emitters. Once you've added both of them, select Finish. Once you've created your Niagara system, rename it to NS Burn. Open the system up and we're going to disable the directional burst so that we can focus on the fountain emitter first. We're going to start by disabling the components that we don't need. So we're going to start by removing the shape location, the add velocity, the gravity force, and the drag. Next up are the two parameters we'll be needing. The first one, a vector called alignment, which we'll leave at its default value. The second one, a linear color, which we'll call color. We're going to start our modifications inside of spawn rate. We'll change the 90 that it's currently at to 200. Next is the initialized particle, where we'll change its lifetime mode from random to direct set and leave it at 1. For the color, we're going to change it to our color parameter. For the sprite size mode, we want to change it from random uniform to uniform and set the sprite size to 5. And to finish, set sprite rotation mode to unset. We're going to be setting up the rotation manually by adding a module in particle spawn called sprite facing and alignment. Once you've added the module, we want to change the sprite facing value with our parameter alignment that we created. The only remaining change we have to do is inside of the sprite renderer, where we're going to change the alignment from unaligned to custom alignment, and set facing mode from face camera to custom facing vector. We can now re-enable our directional burst, and we can disable the drag because it's the only one we won't be using. Then open up emitter state and swap the loop behavior from once to infinite. We also need to set the loop duration to 0, and right now you'll see thousands of particles pouring out all at once. Next, to stop these particles from spawning in such high quantity, we're going to go into spawn burst instantaneous, set spawn count to 2, and enable spawn probability and input 0.2. Inside initialize particle, we want to change the lifetime mode from min to 0.5 and maximum to 1. We also want to attach our color parameter to the color. We also want to change the sprite size mode from random uniform to uniform, but we want to set our uniform sprite size to a random range float by clicking on the little drop down on the right side. Set the minimum to 2 and the maximum to 10. Next up, we want to go to add velocity and reduce the minimum and maximum to 100 and 400. Set distribution along cone to 0, and for the cone axis we want to change x to 0 and z to 1. And finally change cone angle to 160. Next we want to open up our scale color module, and we want to change the scale RGB by getting the small drop down on the right and searching for make vector from linear color RGB. We need to change all the values to something like 15 except for alpha, and this will give us the kind of bright effect of a spark. Next we're going to go and change the scale sprite size by speed. We're going to change the min scale factor to 0.2 and 1, and the max scale to 0.5 and 10. Inside of particle update, we still have one module to add, which is the collision module. Inside this module, we just want to change the bounce restitution from 0.6 to 0.3. And with that, we just finished all the particle effects we'd be needing and all the sound effects, and now we can finally get back to the blueprints. Next, we want to go back into our A_laser so that we can add the particle effects to the Niagara Systems we created there. Simply select the particles by the name of the component you created. Before we start with the blueprints, we want to go into the viewport and rotate our Niagara system for the burn particle. Rotate it 180 degrees on the x-axis so that it's pointing downwards. So now we want to open the function we created earlier called update location burn VFX. The first thing we're going to want to do is we want to set the location of the burn particle effect. So what we're going to do is we're going to drag off the hit result, break the node, and grab our impact point and add it to our impact normal. So we have a slight offset so that the collisions don't hit the walls. Then we want to get our NS burn and call set world location. Connect all the nodes to the set world location. Next, we're going to need to set our NS burn alignment parameter. So copy NSBurn and set vector parameter. Change the parameter name to alignment. Connect impact normal to the parameter. Now, because we added attenuation to our sounds, we also need to make sure that our laser burn is at the same location as the actual burn effect itself. So we grab a reference to that and attach it to our set world location. One extra little detail that I missed in the components is that we need to make sure that auto activate is true for heat wave, but false for burn. Otherwise, we would always be hearing the burn effect even though we're hitting a target that shouldn't burn, like a laser cube. Actually, although that logic holds true, and that we don't want the sound to start, we actually need to activate it automatically beforehand because we need to change its color, so it needs to exist, and then we'll disable it. So re-enable auto activate. So we're going to make this change inside of change color. Get a reference to NSBurn and call set color parameter. Set parameter name to color and set the parameter itself to our variable called laser color. We actually don't want to plug the laser color immediately into the parameter, as we want to multiply it by a certain intensity so that it actually emits light. So we're going to create a local variable for that called L intensity. Set its type to float. And after compiling, we can set its default value to something around 20. And as discussed earlier, now we want to get another reference to NSBurn and deactivate it. With that, we've finished setting up all our new functions, and now we're just going to go and place it around in the different spots that need it. So we're going to start by opening up our update laser size. Inside of the function, we're going to make some small changes to how we calculate the distance, just so we can use it better later for the particle effects. Instead of dividing range by 100, we're going to directly connect the range to the select. Then we'll remove the divide by 100 for the other option for the select, and replace the +1 by +5. And instead of connecting the result to our scale, we're going to promote to a local variable called L laser size. After putting the nodes into the exact top left corner because I have OCD, let's move on and get our local laser size and divide it by 100 before connecting it to our scale. Now let's set up our particle effects. We'll start with heat wave. Now for heat wave, we want to set its world location. To do so, we're going to get a reference to our hit result parameter and a reference to our Niagara System heat wave, which will then drag out and say set world position. So for the location, we're going to need a quick calculation to get the middle point of the laser. So we'll start by breaking the hit results. Getting our end and our impact point, and we'll use a select to see if it's a blocking hit. We'll then add the results of the select to the actor location and divide the total by 2. We're then going to add 50 on the Z-axis because we want the heat to be obviously above the laser in all circumstances. Attach the results to the set world location and make a little bit of space because we're going to set the vector parameter in front. So get another reference to our NS heat wave and drag out and say set vector parameter. Set the name to box size and we can split the pin because we're only going to want to change the Z. And the value we want to plug in is our local laser size. And to finish off, we're going to need to get a set float parameter for the heat wave. Set the parameter value to laser size divided by 100 and the parameter name to spawn rate. If we run the project in its current state, we'll finally start to see these effects that we've created. So let's try and do that. And after running the game, we can hear the sound and we can also see our distortion happening above the laser. Once we're done testing, we want to go back into our A laser and this time we want to open same actor hit. Inside this function, we want to make a bit of space at the beginning because we want to check which actors that we're hitting actually do take in the BPI that we created before. So to check this, we want to check if last hit actor we want to call last hit actor and search for does implement interface. For the interface, we'll be selecting BPI lasers and we'll then add this to a branch. On true, we'll keep our cast to A laser reflect and the rest, and on false, we'll call update location burn VFX. Get a reference to hit results and connect it to the parameter. Next we want to open different actor hit. Inside we want to go down to our second branch where the hit actor does implement interface, and on false we want to get a reference to our audio for the burn and our Niagara system for the burn. And for both of these we want to call the activate function. And we also want to call our update location burn VFX and attach our P hit information to the hit results. And for the final function, we want to go and open our nothing hit. Once inside the function, we want to go down to after our bounce laser. And we want to get a reference to our audio burn and our NS burn. This time with both of these references, we want to call deactivate. Now we can go and test the project to see if it's functioning. There seems to be an issue where the laser isn't cancelling itself when it hits a new actor. But if we move the cube around, we can see that everything else seems to be working just fine. The laser is following when we're hitting the same target. It just doesn't disconnect or disappear when it should. So due to this, the issue likely lies in the different actor hit function. So let's go and open that up. So once we're inside, we can actually see that we don't ever deactivate the laser, even if we hit something that shouldn't be causing the burn. So to solve this issue, on the doesImplement interface of the last hit actor on false, we want to get a reference to our audio laser burn and our Niagara System burn and deactivate them. Let's test the project one last time, and as we can see, the bug that we saw before is no longer there. Let's try moving the cube around to see if the issue reappears. And everything seems to be working. The entire system, the laser, the impact, the sparks, the pulsating and the heat all seem to be appearing with no issues. We just have one last thing to do before this tutorial comes to a close, and that's going to be adding the audio for activating and deactivating. For that, we're going to need to open our laser cube. Inside laser cube, we want to go ahead and open our laser bounce function. Right after the branch on both true and false, we want to call our function activate/deactivate that we created in our parent class. For the true, we want to set the sound to power on. And on false, we want to set the sound to power down. So let's run the project one last time to see if everything's working, and as you can hear, the sound does start, but when we move the cube, it doesn't. The source of this issue actually lies inside of the different actor hit once again. On the true of doesImplement interface for the last hit actor, we want to make a bit of space because we're going to add our laser bounce function. Once we've added the laser bounce function, we want to attach it last hit actor to the target, self to the laser hit, and p hit information to p hit information, and we'll leave hit response as false. Let's run the project again, and if we hit the laser, the cube powers up. If we leave the laser, it powers down. Everything is indeed working, but there still seems to be an issue. When we disconnect the cube indirectly from the cone, it should also turn grey, which it didn't, so let's try and solve that as well. To solve this issue, you need to open our laser parent and the function clear all lasers attached. The issue is caused by the fact that we automatically delete the lasers without ever telling them that if they're hitting an object, to cancel that object too. So to resolve this, we're going to get our last hit actor from the array element and check if it's valid. So convert it to a validated get. If it's not valid, we just destroy the actor. But if it is valid, we want to check if it does implement interface. Add a branch and then set the interface to BPI lasers. From our last hit actor on true, we want to call bounce laser. Set laser hit to the array element, and the other two can be left empty as it's a negative hit response. On false, we also want to simply destroy the actor. And with that, this hour-long tutorial is finally finished. Congratulations for anybody who stuck to the end. I don't know how I pulled it off to even make this tutorial. It's way too long, and this is definitely the last time I'm making such a long video. But I hope you enjoyed nonetheless, or at least learned something and was able to polish your laser. Thank you again for watching, and I'll see you in the next devlog or tutorial, whatever comes next.